Hi, we're the team Hacktivists. Okay. Our team solved the problem of having a difficulty in creating accurate 3D models because of the challenges due to high cost of creating professional grade equipment, limited detail in depth camera only solutions, and also the lack of integration between depth cameras and photogrammetry.
So we rolled out our piece of plasticine clay, and then we took two straight wood pieces on the sides so that we were able to keep our plasticine level and keep the sides straight. Then what we did was we took the end of the tool, we used scalpels and an X-Acto knife to carve out the heart shape, and then we used a water bottle to press down to distribute pressure evenly and create a lower level. So our initial approach was to develop an affordable and efficient system for room mapping. Then what we were going to do is combine depth data from the Arducam TOF and the photogrammetry for high detail models to create a workflow that's accessible to hobbyists, researchers, etc. So for our components, we decided to use an Arducam TOF camera. We decided to use a Raspberry Pi, a computer for processing depth data and photogrammetry, and we used these components because they were affordable, widely available, and easy to integrate with open source tools.
Capturing overlaying images. And then finally, we did data integration by aligning the merge point clouds in Cloud Compare. The first input stream, we used the Arducam TOF, which was the depth camera. Our first technical implementation was basically taking a raw depth matrix from the Arducam TOF and then converting that into a point cloud using Python's Open3D library. The second input stream, we captured the iPhone data, put the images in Meshroom, which would output a 3D surface mesh, and we would either import the Meshroom point cloud or the Cloud Compare mesh into an integration with the data from the depth camera.
So we used the Arducam's data, imported that into Meshroom, and we combined all of the data to make a 3D model. Obviously, the model was way too noisy to be actually used, so we stuck to the iPhone models.
Our team also developed a website which highlights all of our features. Please check it out.
Since we need to be able to calculate the strain on our plasticine, we decided to utilize the iPhone's LiDAR photogrammetry system to manipulate the data. We used NumPy and OpenCV to be able to calculate our strain points, the process and how it works. So what we did was we had to detect the fiducial points, compare the before and after images. We highlighted the deformation and we visualized our results. This matters because we use a system to remove the noise, create a more accurate strain measurement, and improve our visualization. Our end result, we have a before forming, after forming, and the strain difference. For figure 1, what we did was we took a pencil at a certain amount of distance, we poked our model and created a strain. We have the before and after, and the strain difference that clearly shows the difference that actually happened. In our next page of our in our next strain optimization strain thing, what we did was we broke half of the model off, and we wanted to see the strain difference, so that our model perfectly maps that as well. We can clearly see the strain difference between the left half and the right half and the missing portion. Yeah.
Thank you.